All right, so if you recall, when we were talking about factors that affect climate, one of the factors affecting climate was proximity to oceans, right? And we noticed that places like Victoria and Vancouver, even though they have similar latitudes to, like Calgary, their climate is a lot more mild. Okay, they don't get severely cold winters. Okay, they don't get snow very often. Okay, temperature doesn't fluctuate. In fact, they don't really get really hot in the summertime either. Okay, their temperature is very regulated. Okay, and it's the ocean that regulates that temperature. The reason the ocean regulates that temperature is because water has a very high specific heat capacity. What that means is water can hold on to energy. Not so much hold on to it. When water has to gain or lose a lot of energy in order for its temperature to change. Okay, so if I'm in a place like Victoria where I'm right next to the ocean, okay, and the air starts to get cooler, the second law of thermodynamics says that energy will have to go from the ocean to the air. Okay, like if air temperature starts to drop and the air is over the ocean, okay, then energy is going to move from the ocean to the air. Okay, the air and the ocean cannot be all that different in temperature. The second law of thermodynamics says anytime there's a change, energy is going to flow from hot to cold, and the ocean's always going to be a bit warmer. Okay, so we're going to have energy always flowing that direction. That means that the air temperature can't really drop below what? Below the temperature of the ocean, and definitely not below freezing. Okay, I mean, it does occasionally, but we're still talking about a situation where energy from the ocean would move into the air. Now, the thing about that is that the ocean can transfer a lot of energy to the air, and its temperature, the ocean, doesn't change very much. The air's temperature can change a lot, okay, but the ocean's temperature won't change very much, which is why being next to the ocean can regulate or moderate your temperature. Okay, and not allow it to fluctuate a whole bunch. Okay, everyone kind of follow me on that? Okay, that's because water has a very high specific heat capacity. And what we mean by that is specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, for water, that number is 4.2 joules per gram degree Celsius. Okay? That means if I have 1 gram of water, that's 1 milliliter. Okay? So that's a very, very small amount of water. It takes 4.2 joules of energy to change that small amount of water's temperature by 1 degree Celsius. So if we're talking about an ocean, which is, billions of tons of water, okay, we're talking about there being a lot of energy in there. And so if it's losing or gaining any energy, okay, it can lose or gain a lot of energy, and its temperature doesn't change very much. Okay, so that's where that whole factor affecting climate thing comes from. Okay, now heat capacity is the term we use if we're talking about an object. Okay, because an object might be made out of a bunch of different materials. So if we're talking about like a pan, for example, okay, the pan might be made out of an alloy that's a mixture of a couple of different metals, and it would have a handle that's made out of plastic or whatever. Yes. Okay, so if we're talking about heat capacity, that's the amount of heat required to raise the temperature of an object by 1 degree Celsius. Notice there's no mass here. Okay, we very rarely ever talk about heat capacity. Most of the time we talk about specific heat capacity, we're talking about a specific material. Okay, each material has a different heat capacity. That's why we call it specific. Okay, each one is different. Okay, water, like we said, has a very high heat capacity. Right, Liam? Okay. Yeah, chug that coffee, dude. I feel your pain. I'm tired too. All right. So the formula we use to calculate the amount of energy that would be required to change the temperature of something is this one. Okay, E equals m times c times delta T. Okay, where m is the mass of the substance in grams. Okay, c is the specific heat capacity in joules per gram degree Celsius, and delta T is the change in temperature in degrees Celsius. Okay, now, is this a fairly easy looking formula to use? Everything is being multiplied together. So if I need to manipulate it for anything, what do I do with everything else? Just divide it over to the other side. Okay, it's really easy to manipulate. If I need to solve for M, I divide C delta T over to the other side. If I want to solve for C, M and delta T get divided over to the other side. It's really, really easy to use. All right. Okay, so like we said, E is the energy in joules. Okay, M is the mass of the substance, and it's in grams. Okay, delta T is the change in temperature, and that's in degrees Celsius. Okay, and C is our specific heat capacity, which we said is in joules per gram degrees Celsius. All right, so that's what we need to know about specific heat capacity. Okay, its role in as a factor affecting climate. That's the biggest thing we need to know about it. Okay, then we do some easy problem solving. Okay, using the formula. Okay, because it's going to be pretty straightforward. All right, so anytime I give you a new formula, I go through all the manipulations of it. So copy this one down. This is the first example problem for using MC delta T. Okay, give you a minute on that one. Okay, so looking at this question here again, first thing we always want to do is write down our givens. The question wants to know how much heat or energy, right? So we're looking for the amount of energy, okay, is needed to raise the temperature of 150 grams, so they told me the mass, okay, of water, whose specific heat capacity is 4.2, okay, from 5 degrees to 85 degrees Celsius. So what's my temperature change? 80. All right, so I have M, I have C, I have delta T, and I'm looking for E. So this is the easiest of them. I don't have to manipulate the formula. I just need to plug in my numbers. E equals M times C times delta T. So that'll be 150 grams times 4.2 joules per gram degree Celsius times 80 degrees Celsius. Oh, missed the 2. All right, so that's going to take 50,400 joules. Okay, or 50.4 kilojoules worth of energy. Right, so if you're heating up water on the stove, it takes a lot of energy to do that. Okay, heating water, cooking anything, okay, takes a lot of energy. All right, questions on how that one worked? Yeah. Yep. Any other questions on how that one worked? All right, copy this one down. This will be our second example problem for that. Okay, so we'll start this one out the same. Okay, we want to write down our givens. The question is asking what material this stuff is made out of, which means I'm going to be looking for the specific heat capacity. Now, for you guys, I do have a list of the specific heat capacities, and it's in your it's in the workbook for this unit. So you'll need to have that open when we're doing problems of this nature, okay? But it'll be in there. Come on. So it's right here. It's the first page, okay? There's a list of heat capacities of common substances. All right, so what we'll do is we'll solve for the heat capacity in this question, and then we'll just look for it on here and figure out what material it goes with. Everybody kind of follow me on that? Okay, so we're looking for C. And we know that it takes 4,200 joules of energy, so they gave us E, okay, to raise its temperature from, oh sorry, and they told us the mass, 100 grams, I missed that, okay, from 12 degrees to 62 degrees Celsius. So our change in temperature is 50 degrees Celsius, right? So we're looking for C. So our formula starts out as E equals M times C times delta T, and I'm looking for C, so I divide over everything else. So the delta T and the M end up over here. Now, when you punch this into your calculator, it's important that the bottom is done as an entire operation. Okay, otherwise your calculator will do it from left to right, which doesn't yield the same or correct answer. Okay, so we will have 4,200 divided by 100 times 50 degrees. All right, so we're getting a specific heat capacity here of 0.84 joules per gram degree Celsius. All right, considerably less than water, right? Like more than 4 times less. Now, if we look on our chart here to see what it matches up with, 0.84 is glass. All right, so the material that was being heated up here is glass. Okay, questions on that one? All right. This is about as tricky as they get. So copy this one down, and then we'll walk through it. So the trick with this one is it's asking us for the final temperature, which is not one of the variables. Okay, the only variable that's close to that is change in temperature. Right? If I want to find the final temperature, I'll probably need the change and I'll need the initial. Yeah, and they give me the initial. They tell me it starts at 7 degrees Celsius. All right, so what I'm going to write here for my givens are that I have the initial temperature being 7 degrees Celsius. Okay, I don't have the change in temperature, but I can find it because I have the mass. All right, they told me it was 185 grams. Right? They told me that it's iron, so I can look on my chart here and find that iron has a specific heat capacity of 0.460 joules per gram degree Celsius, and that we're using 200 joules worth of energy. All right, so that's what I have. So E equals M times C times delta T. So I'm going to find delta T. That's what I'll do first. So I'm going to divide both sides by M times C, okay, and I'll have this. So 200 divided by 185 times 0.460. All right, so we're looking at a temperature change here of only 2.35 degrees Celsius. Okay, so what's my final temperature? 9.35. Okay, and the way I do that is I just said, all right, my change in temperature is like anything else. Temperature final minus temperature initial. If I want to find the final temperature, I add the initial to the change. 7 plus 2.35 is 9.35 degrees Celsius. Okay, that's as tricky as they get because it has that extra step at the end where you have to find the change in, where you have to use the change in temperature. Okay. Questions on that one? Okay. All right, so I'm going to have you working on, from the workbook here now, a few problems to do with that kind of thing. Okay, I'll make it a little bit bigger, but you might want to call it up on your phone. Okay, so we'll start out with these, and here's my suggestion. They go in a weird order. The first 5 questions are all about finding C, and then the next 5 questions are all about finding the energy, and then the next 5 are about blah, blah, blah. So what I would say is do like 1, 6, 11, okay, so that you're getting one of each kind. All right, that would be my suggestion, okay, just so that you don't end up doing 5 questions that are basically the same. Then you can go back and do 2, 12, 2, 7, 12, okay, and so on. All right, so I'm going to give you some time to get going on those, and then we'll go over any ones that give us trouble. Okay, so for number 11, okay, we're boiling water to make Kraft dinner, okay, and she applies 60,000 joules of energy. So we know E is 60,000 joules, okay? It's 1.4 kilograms of water. How many grams is that? 1,400. It does have to be in grams. Okay, kilo always means 1,000. Kilometers is 1,000 meters. Kilograms 1,000 grams. Okay, how much does the temperature increase by? Okay, well, we also know that it's water, so we know the C is 4.2. Right, so we're looking for delta T. So delta T will be E divided by M times C. So that'll be 60,000 divided by 1,400 times 4.2. Right? When we do that division, we should get 10.2 degrees Celsius. Okay? Any other ones giving us trouble? That's about the only dirty trick you're going to run into on these kind of questions. Okay, is that I give you the mass in kilograms because it's a large number instead of grams, and you just have to convert it. Okay, so for tomorrow, okay, tomorrow we're going to be working on latent heats. Okay, which has to do with latent heat, that stuff that transfers all that energy. We're going to be looking at that specifically tomorrow. Okay, and Friday, I will probably be looking at maybe even your unit exam review, okay, or possibly another short lesson, and then do the unit exam review on Monday. And then you've got a unit exam, okay, coming up after that. But we still got a couple of things. We're going to do a lab, on Monday. Doing a lab on Monday on latent heats. That lab will not be coming in for homework. Okay, we're going to do it all in class. I'm not going to take it in for marks. We're just going to do it so that we have it because there's some questions about it on the unit exam. Okay, there will be a quiz tomorrow. Yes. Okay, probably we'll have some specific heat questions on.